So let's get started. I'll begin with a word of prayer. Dear Heavenly Father, we thank you again for this day. I thank you for these students. Pray be with us today. Help us to understand the material. I just pray that the material that we cover today would really sink into the students' brains and just stick there. They'd be able to remember the rest of the semester. I know these things are really important. And I just want each and every one of these students to succeed, Lord. Pray that you be glorified in what we do here this day. In your name I pray. Amen. All right, I'm gonna start with a game. A game, yeah. You guys are gonna like this game. Yeah. Oh, I'm not sure. It's been a while since I played this game, though. So you guys, I'll start out. I'll put in there. So you guys go ahead. You pick a letter, any letter. A. Nope, no A. I. We have two I's. There is no E. Haha. I will. It's what? Yes, limit. Oh, yeah. And so, yes, in fact, if you think of this as limits, this is what's happening. So that is what's happening today. Limits are dying. I'm eliminating them. Ooh, there's a pun in there. That was unintentional. Oh yes, there's always applause when I remove some controversial mathematical topic like limits. What if I like limits? Like, I don't know. See, math is difficult this way, right? You know, if I showed you guys, suppose I had a wallet, and I guess I have a wallet. But suppose I actually had pictures of my children in my wallet, and I pulled them out and I showed them to you, and your reaction was, they're hideous, right? You would never say that to a person, right? But the general population is more than comfortable anytime I express my love of mathematics of going, why? Right? You guys are totally fine with that. It's a very select class of people who rejoice in their ignorance about reading. Right? You won't find many people who are like, yeah, I can't read. Whatever. But how many people will be like, yeah, I'm not good at math. I can't add. I can't do fractions. Like, people are proud of this. What's wrong with our society? What is wrong with our society? So today I'm going to talk about differentiation. Are you going to solve that equation? Which equation? Oh, the equation. You guys are supposed to write that on the board before class. Therefore, we shall solve the equation. All right. This will interrupt the flow of my lecture. But what was the equation? Okay, my box is not big enough. So I invited you guys to do that at the end of last class. I will now show you the solution, since you reminded me. So let's see here. F prime of 3. And I'll use this as x goes to 3. And I do this f of x minus f of 3 divided by x minus 3. I'm going to use that form of the difference quotient. And let's see here. So what is that? That's the limit as x goes to 3 of, see, I just got done to this long song and dance about how I wasn't going to do limits anymore, and then see how awkward this is, what you've done to me. Okay. Okay. I showed him. All right. Kind of sass. Yeah. What I need is like a bucket of Kool-Aid. somebody to go up to the top. See here. Okay, so we multiply by the rationalization. So like you do x plus 2 minus, not minus, but plus the square root of 5 over the square root of x plus 2 plus the square root of 5. I'm going to try to go fast through this because I want to go slow through the other stuff today, if that's all right. So the reason we do that, of course, is that upstairs we end up with x plus 2 minus 5. And downstairs we end up with x minus 3 times the product of x plus 2 plus the square root of 5. The reason for that, of course, what makes that awesome is that the numerator, I can simplify to what? This is really just x minus 3, right? So these reduce, and you're just left with 1 over the square root of 3 plus 2 plus the square root of 5, which is otherwise known as 1 over 2 times the square root of 5. And there you have it. So you use the rationalization of the numerator algebra step, which is why I gave you guys those homework problems at the start of the course about rationalizing numerators and rationalizing denominators, because that's what you need to do to actually calculate one of these derivatives from the limit. In the first step, that's the definition of the derivative. This here? That's just from here. So I'm just, this f of x minus f of 3 is this. That x minus 3 is this x minus 3. This I multiplied by 1. 3 plus 2 is square root of 5. Yes, sir.
So why do you not plug in? Come back.
Okay.
Like the x minus 3 at the beginning of the problem.
Yeah.
Why is that 3? You don't plug anything in for that until the end. Or did you ever plug in it? Has that already solved before?
So I have to look at the difference quotient, which is f of x minus f of 3 divided by x minus 3, right? That's the change in y over the change in x. As x approaches 3, it gets us the infinitesimal rate of change as x approaches 3, right? Which we call slope of the tangent line, or the derivative at 3. This has division by 0 to start with because this is 0 over 0. But when I multiply by this, the square root plus the square root pattern, when I multiply that out, I get x plus 2 minus 5, which gives me this x minus 3, which is really nice because then that cancels with the x minus 3 downstairs, just leaving me this expression, which I can plug in the limit point, and I don't have division by 0. I can just evaluate the expression that we come to at the end after the algebra step.
So you always put in the limit point after you have like a rational fraction that you plug it into the end, or what?
Yeah, we can't put the limit point in until we've done algebra to remove the indeterminacy. Like the indeterminacy of this limit is type 0 over 0. So I have to find some way of like factoring out 0 on the top in some sense so I can cancel it out. For this, the factoring out 0 was accomplished by multiplying by the square root of x plus 2 plus square root of 5. That uncovered the source of the 0 in the numerator, which was actually x minus 3. Yep. There was a, yep. Fight for it. Some more. So square root of x plus 2 times the square root of x plus 2 gives me x plus 2. These cross terms cancel, right? Because I get plus square root of 5 minus square root of 5. And then I've got square root of 5 times square root of 5, which is 5. But there's a minus. So I get plus x plus 2 minus 5, which is x minus 3. I had another step there that I erased because I don't want to write too low on the board. Sorry about that. Yeah.
If it were to be like f prime 5, would that make it as x approaches 5?
Yes, f prime of 5, I would replace the, I put a 5 here, I put a 5 here, I put a 5 there. Yeah. Wow, you guys got lots of questions today. Go ahead.
Why is there a difference between using this and then plugging in the 8? Is that because we're asked to find f prime of 3 instead of just finding the derivative?
There really is no difference between saying x approaches 3 and h approaches 0. It's just a different way to calculate the tangent line. Admittedly, the one in your book is the h goes to 0, but I thought it would be good to do one of the other kind because sometimes this is a lot easier. Let me show you. Now, I said limits are dead. That's almost true. It's almost true. They'll be pretty much completely dead by the end of today, except on your test, of course. But oh man, yeah, I know. But I do ask you how to. I will have questions on the test, which are of the format: calculate the derivative from the definition, which means involving limits. I'll be quite explicit about that on the test when I want that. But let's look at an example. A little bit easier. How about f of x equals to x? All right, really simple function. What is f prime of x equal to? Limit is x minus a. X goes to a. Oh, sorry, f prime of a. Right. X goes to a of what? So in my current notation, it's f of x minus f of a over x minus a, which is what? Not 0. Oh, you got it? Okay, yeah. Close, though. I mean, 1 is pretty close to 0. Oh, you almost got me to put 0 there. Oh, my goodness. What are you doing to me? 1. Now, another notation for this, guys, is simply the following. We have shown that the derivative with respect to x of x is equal to 1. I mean, well, fine. I guess I'm uncovering the reason your book uses h. I see it now. I mean, it's not necessary, but fine. Here, I'll show you why they use h. So let's let, next example, let's let f of x equals to x squared. All right? Let's calculate the derivative of that. So what's f prime of a? If we use my silly not h but x goes to a based thing, we do what? X squared minus a squared over x minus a. What, you see what I did there? I just skipped the step of writing f of x minus f of a over x minus a, right? Because if f of x is x squared, this is f of x, this is f of a, there you have it. Can you factor x squared minus a squared? Okay. What does it factor? Difference of perfect squares, right? So the x minus a factors reduce, cancel out, yeah? And we're just left with what? Limit as x goes to a of x plus a, which is equal to what? A plus a, or 2a. So what this calculation shows us, we find f prime of a is equal to 2a. All right? And so you guys, it's easier to think about the derivative function if we use the letter x, right? So this then changes to f prime of x is equal to 2x, right? So there you have it. Or if you use the differential notation, the derivative operator, which is a nice notation, we have d dx of x squared is equal to 2x. So we think about differentiation is something we can do to an expression to produce a new expression. If I differentiate x squared, I get 2x. If I differentiate x, I get 1. Yep.
So how do you know whether to use the formula you're using there or the f of a plus h minus f of a over h?
Well, that's a good question. I mean, you know, it's a question of taste, really. We could do the same example with the other one, but instead I'll do the cube. F of x equals to x cubed, right? And I'm going to do what you said. And here's the advantage of using the h notation is I don't have to have this extra step about a. I can just say, aha, limit as h goes to 0 of f of x plus h minus f of x over h. And I guess that's the reason to not use the a notation with you guys, is it just avoids an extra step. you guys might get confused about the difference between A and X. Yes, either, yeah. I'll use H now. H goes to 0. F of X plus H minus F of X. For X cubed, what is this? I think that the algebra doesn't work out quite as easy with the H is my point, though, guys. So X plus H quantity cubed minus X cubed divided by H. That's the limit I have to deal with this time.
So for those, I think you just said it, but the A is 0 for that?
No, A was here, in both of these examples, A was an arbitrary real number. Could be anything. A was for anything. I don't know. I just made that up. So how do you cube something? You guys know Pascal's triangle? So this shows you the coefficients to put next to the terms as you like FOIL them out. So you guys know this, for example, tells me that X plus H quantity squared is X squared plus 2XH plus H squared. And so this row right here in Pascal's triangle, you see how you get the term, you add the things above it. So this would give me X cubed plus 3X squared H plus 3XH squared plus H cubed minus X cubed. That's what happens when you cube that thing by Pascal's triangle. Some stuff cancels. What are you left with? Yeah, the X cubes canceled, and you've got H's in what remained, right? So we get, if you look at that, we get 3X squared plus 3XH plus H squared. Again, the X cubes canceled, and if you look at everything that we're left with has an H on it. So I can divide by the H downstairs and remove 1 power from each H. H goes to 1, H squared goes to H cubed goes to H squared. And that is something we can calculate the limit of. What's this equal to? Yeah. Oh, yeah, okay, these terms go to 0 because H goes to 0. But this thing is just constant, and that survives. So the limit is 3x squared. In other words, the derivative of this function is 3x squared. Or to be more, to use our other language, the derivative with respect to x of x cubed is equal to 3x squared. So to answer your question about A versus H notation, I mean, if you had done this with the other notation, instead of facing this algebra, we would have faced this algebra. And some of you might already know that that's equal to x minus a times x squared plus ax plus a squared. Because that's something some people teach in college algebra. So you wouldn't have actually had to cube the thing, and you would have been able to factor it out if you know your third order factoring stuff. And then that would have just divided, left you this, and then that would have gone to a squared plus a squared plus a squared, which would have given us 3a squared. Then we would have changed the a to x in the next step, thus giving us the derivative of x cubed is 3x squared. Anyway, I shouldn't have to do each example twice. This is kind of defeating the point of talking about both notations. Yeah. Oh, soon, but I have to explain where those come from, right? That's what I'm doing.
Is that a shortcut?
We're getting to that. I have been using some color coding. I know what you want me to do is to erase everything on this board except for what's in red. Am I right?
No, I just meant, are we going to be questioning on the test?
Both. But I will be very, very clear about which I want from you, because I know that. I mean, okay, there may be some problem where I say I don't put limitations on you. You could use either approach. If you guys don't know what she's talking about yet, you will soon. So if you, so her question is essentially this. She's asking, when can we just essentially use the formulas that are in red to do the differentiation? When do I have to go back to the limiting process? And how do I know which one to do? The answer most certainly is you want to just use the red boxes if it's allowed, for sure. That is the way to go. So what I'm trying to do for you guys here right now is to motivate those red boxes to show you where they came from. They come from these difference quotients. But I think you've seen enough, right? So now I'm just going to tell you the rest of the story without proving things, if that's all right. I mean, whether or not it's all right, I'm going to do it. So do you see any pattern here in the ones we've done so far? These are all examples of the what? The beloved power rule. What's the power rule say? It says the derivative with respect to x of x to the n is simply equal to n times x to the n minus 1. Here we have the derivative with respect to x of x to the first power is equal to 1 times x to the 0 power. X to the 0 power is 1. So there you go. This is the power rule, n equals to 1. This one that we worked out is the derivative of x squared, right? That's 2 times x to the 2 minus 1. Well, 2 minus 1 is what? It's 1. Yes, I think we got that. So this is 2x. So this is the power rule, n equals to 2, n equals to 1. This is n equals to 3, right? The derivative with respect to x of x to the third power is equal to 3 times x to the 3 minus 1, which is 3x squared, right? The reason these are true, though, goes back to some difference quotient, which we would soon like to forget. We don't want to forget it's there, but we certainly don't want to keep calculating it, because it's a drag, right? In fact, I would argue this. If you guys always had to calculate the limits, if you actually had to explicitly calculate limits for calculus, we wouldn't teach it as a freshman course. It would be something that was reserved for an elite class of people called mathematicians who could understand these things. It certainly wouldn't be something we would try to teach the general population because it would be too technical. This is not technical. This is just algebra, right? I mean, we can do this all day long and not hurt our heads too much, I don't think. Now here's the kicker, though. While I showed you the proof for n equals to 1, n equals to 2, n equals to 3, this is in fact true for any exponent. This is true for n, a real number. I'm not going to be able to prove that in here, but if you'd like to, I can, I said any real number. What did I write? Natural number. Idiot. Real number. Oh, sorry, I'm still telling you things. For n, a real number there. I think I can safely write that. But now you're probably thinking I'm saying for a not real number. I don't know what to do. Okay, let me calm down here for a second. Let's look at 10 examples. Example number 1. Derivative with respect to x of 1. What's 1? X to the 0 power, right? So we have what? 0 times x to the minus 1. Which is just 0, right? Now, of course, we kind of know that from more basic principles. What does d dx do? It's calculating the change in the expression with respect to x, right? Does 1 change with x changing? 1 is 1. No, 1 doesn't care if x changes. It's just 0. It doesn't change at all. That's why we get 0. 2, how about this? The derivative with respect to x of x to the minus 1. Well, let me do it. They don't usually come for you all nice and pretty. How about the derivative with respect to x of 1 over x? What's the name of the game here? First thing you got to do is rewrite it as x to the minus 1. Right? Identify, this is power rule, so I go minus 1, x times x to the minus 1 minus 1. What's minus 1 minus 1? Yeah, minus x to the minus 2, which I personally like to write as 1 over x squared. I think that's how I like to think of this for future purposes. Another very common example. The derivative with respect to x of the square root of x. Yeah, so first step, rewrite it as what? 1/2. And then I do what? 1/2 x to the 1 minus 1/2, right? What's 1 minus 1/2? Oh, I'm an idiot. It should be 1/2 minus 1, right? Good grief. I have to go stand in the corner again pretty soon. Let's see here. 1/2 x to the what's 1/2 minus 1? Yeah, negative 1/2, right? Now, that's a fine answer, but a better answer is that this is 1 over 2 times the square root of x, because for some reason the square root of x is a more familiar function, so, that last expression I wrote is that's what I think of. I don't even go through the power rule at this point in my life, guys. If I see the derivative of the square root of x, I just know 1 over 2 times the square root of x. It's kind of worth memorizing, honestly. It comes up a lot, yeah.
So we did, I took calculus last year, and you had us memorize the last group there. Are you going to have us do that, or do you want us to actually go in, like if we're taking a test, we have to show and plug into the n minus 1 and that stuff, or could we just get over it?
If you know it, you can just write it down. It's fine. Yeah. I will not make you suffer the details there if you don't want to. I'll try to ask something else that will force you to write the details. It's not hard. Yeah.
Should I have taken calculus last year?
Should you have taken calculus last year? I don't know.
I failed that.
you failed it.
I did pre-cal last year.
I don't know, guys. How about the cube root of x? So
Really, taking pre-cal right now.
these labels, pre-calculus, algebra 1, algebra 2, pre-algebra, I don't know what they mean. I have no earthly idea. So let's see here. Well, I'm just saying that there's so many different curriculum schemes. Who knows what those words mean? One person's pre-calculus is another person's college algebra part 2 or part 1, or who knows. 1/3, x to the what? And so very soon, guys, I get tired of writing that thing and I just do it in my head. 1/3 minus 1 is minus 2/3. You don't have to write the 1/3 minus 1 step if you don't want to. But beware, it's where you guys usually make a mistake. I am being somewhat stereotypical in my comment, but it's kind of what math is about. Math is very stereotypical. I'm sorry, it's true, but like x is x, right? There's no room for individuality with x. Sorry, I digress. Can you guys think of another thing to do here? How about d dx of x times the square root of x?
X. Power x.
1 plus 1/2 is equal to 3/2, right? That's x to the 3/2 power differentiated. So 3/2 x to the 1/2. Would it actually be what? Okay. Yeah?
On number 4, how did you get -2 to the -2 over 2/3 power?
1/3 minus 1 is equal to 1 minus 3 over 3, which is equal to minus 2/3. It's the power law. But again, it's a power rule with n equals to 1/3. Yeah?
For example, 5, do you want us to like write it as number 3? Am I like that? So like 2 over 5, 3 over 2 times that last.
I don't, whether, it doesn't bother, I have no, listen, to me, like just to go back to this, the reason I write 1 over 2 times the square root of x is sometimes it's useful as you're thinking about a formula to think of it that way. But I would count this or that full credit on the test. I don't, I don't have any kind of like secret, this is the correct answer and I'm going to take the other one's credit off. For me, the issue is can you do the calculus? I don't have a well enough developed sense of what's a simplified answer to impose it on you guys. So now, that said, if I do want to force it on you, I would do something like leave your answer in such and such a format. Like here's how I could do that. Here, let me put this next example in that annoying format. So calculate A and B for which d dx of 1 over x plus 3x is equal to a x to the b. See, if I ask the question like that, I can essentially probe whether or not you understand how to simplify things. I mean, it's probably better to make you guys always simplify. You guys come from such disparate backgrounds that it's hard for me to judge what you've been taught before. And if you've been taught this is the correct format for something, I don't want to tell you something else is the correct format and then try to break your brain about it. And yeah, it's just easier to agree that mathematically these are equal. So why not take both as answers? I'm grading your test. I know they're the same. Don't worry. Right? So how do we do this? We actually need another rule here. I told you the power rule, but there are actually 2 other rules that we would like to know. The other rule we want is so-called homogeneity, although your book may not call it that. Homogeneity simply says that if I have the derivative of some constant times a function, I can pull the constant out of the differentiation. And then there's also additivity. Additivity tells me that the derivative of a sum of 2 things, f of x plus g of x, is the sum of the derivatives, assuming, of course, both exist. Taken together, both of these things, homogeneity and additivity taken together, I just grossly refer to as the linearity of the derivative. So these 2 together give us what's known as linearity of the derivative, which in common speak simply means that you can break up derivatives across sums and you can pull constants out, which is pretty awesome. Now that matters to us. I'll let you catch up with that, but let's see here. So this problem, this is really d dx of what? What's x plus 3x is what? 4x, right? And so this is really 1/4 times the derivative with respect to x of 1 over x. But we just worked this one out a second ago. What's the derivative of 1 over x? I'll go through it again. Yeah, negative 1 over x squared. Because if we differentiate x to the minus 1, we get 1/4 times, minus minus 1, minus x to the minus 2, right? Or if you like, if it helps you, I can write minus 1 times. All right, so let me clean it up. What we have then is minus 1/4 times x to the minus 2. Right? So what's a and b? So if we compare this to a, x to the b, what's the x and what's the? We have a equals to negative 1/4, and b is equal to negative 2, right? So that's how I would fairly assess, like, kind of the scratch. That's how I'd scratch the itch you're kind of talking about. Oh, I promised 10 examples. Let's do another one. 7.
Are you ever going to do something like that in 6?
I just did.
I know, but on like a test. So yes, because you wrote it on the board.
ddx of, how about x plus x squared plus x cubed is equal to what? So the rule is you can just successively use the additivity to break it up. This is ddx of x plus ddx of what? X squared plus ddx of x cubed, which gives us what plus what plus what? 1 plus 2x plus 3x squared. There you go. Let's see here. What if we had to differentiate with respect to x? X plus the square root of x divided by x squared. Oh, x cubed, let's say. What's that? We don't know that. What's the quotient rule? What are you talking about? What's a quotient? That's crazy talk. Actually, you're right. We could use a quotient rule, but even when we know it, it'd still be better to do what I'm about to do. So quotient rule can hurt you. Kind of like this example over here. I think there's something called a product rule, I've been told. And you could do the product rule here, right? But that would also be hurtful. Like, this is way easier than doing the product rule. So here, the easier thing to do is do algebra. See, this is x over x cubed, right? I can break up sums in the numerator. Just a comment here before I go further. This is very different than if I had x cubed divided by x plus the square root of x. See, this is quotient rule. No way around it. That's quotient rule. I have no choice but to use the quotient rule there, because I can't break up a sum in the denominator by algebra. But in the numerator, you know, the laws of algebra allow me to break up like this. And then the exponent laws, what we have here? ddx of what? X to the minus 2 plus x to the what? What's 1/2 minus 3? No, the answer is not hammering. Sorry. 1/2 minus 3, let me remind you, is 1 minus 6 over 2, which is minus 5/2. All right. So by that little bit of arithmetic, and so what do we get? We get minus 2 x to the minus 3 minus 5/2 x to the minus 7/2, right? Because if you subtract 1, it's like subtracting 2 halves. And there you have it. No quotient rule. And no, I don't require you to rewrite it in terms of positive radicals. Like, you can leave a negative radical. That's fine. I usually will say something in the preliminary instructions to the derivatives. Differentiate. Do not simplify. I actually don't want you to simplify a lot of times.
Can you explain the last step one more time?
From here to here?
Yeah.
Sure. What we're doing, what we just did there, is I used additivity, and I had power rule n equals to minus 2 for the first term, and I had n equals to minus 5/2 for the second term. So, see, I mean, you understand this piece? Differentiate this, I go minus 2 comes down, that's the n, and then minus 2 minus 1 is minus 3. Minus 5/2 comes down, that's the n, and then I have to take minus 5/2 minus 1. Well, minus 5/2 minus 1 is minus, okay, I got it. Okay. 9 d dx of pi squared. Number 10, d dx of, let's see here. Oh, I don't know, it's just for giggles. X squared plus 2 to the 4th power. I often get Calculus 131 students with this problem. About 30% of the, next calculus class above this one, they will tell me that the answer is what? 2 pi. It's not 1. Pi squared, it looks funny, but it's just a number. I mean, an astrophysicist will tell you this is 10. It's 3.14 quantity squared. I mean, it's a number. It does not, this is 0. Because you could, well, in terms of our current technology, I could say, well, that's the same as pi squared times d dx of 1, right? Because pi squared is 1 times pi squared, so I can pull out the pi squared because it's a number. And the derivative with respect to x of 1 is just 0, as we talked about before. But there's a more general principle. The derivative with respect to x of a constant is just equal to 0. So let's just kind of remember that, because this is a silly calculation and we don't want to keep doing. Now, number 10 with your current technology is kind of a pain. Pretty much the only, what's that? Chain rule? Well, I don't know what the chain rule is, though. The chain rule. Yeah, there is that chain rule. Don't worry. We do not have the chain rule on test 1. The reason for that is it takes you guys a while to get up to speed on the chain rule, because it's about the composition of functions, and it's just a little bit more tricky than the other things we're doing today. So the test 1 will involve power rule, linearity, and yes, also the product rule and the quotient rule. And then the material from before, the definition of the derivative, the limit laws, and of course your basic algebra review. Hopefully with a focus on the new material. All right. You see, if I ask you a good question about derivatives, I'm automatically testing the algebra. So why should I test the algebra separately anyway? Right? I ask you this question. You can't do this unless you know how to work with the exponent laws, right? So this one, though, here's what you do. I would use Pascal's triangle. 1, 1, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1. So this is really the derivative with respect to x of x to the 4th plus 4 times 2 x cubed plus 6 times 2 squared x squared plus 4 times 2 cubed x plus 2 to the 4th, which is what? Well, I'll just write it as 2 to the 4th. Who cares what it is? It's 16, but it differentiates to 0. So the answer is 4x cubed plus 8 times 3 is 24, x squared plus, let's see here, 12 times 4 is 48x. What's 4 times 8? 32. Anyway, I know if I was to ask that question on your first test, I need to leave about 10, 15 minutes for you guys to multiply it out carefully, right? I don't really expect that you know Pascal's triangle. I'm just showing you that if you do, you can multiply stuff out really fast. Now, that's admittedly a recreational example. Like, that's probably not on the test, okay? I don't usually say that, but for the sake of, oh man, I got cookies for you guys today. I forgot to bring them. I know. How many of them, how many people are there in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Yeah, I got enough cookies. All right, I know what we'll do. Let me finish covering the material I need to cover today. Then I'll put a couple examples up on the board for you guys to work. And while you're working those examples, I will go get you a cookie. That's right. Listen, you can't do too many practice problems here. It is so important. This is the most important section of all the sections we've covered so far. Getting the power rule down with confidence and clarity is the bread and butter of the rest of the course. If you don't get this down, you will be fighting it the rest of your calculus experience. It is so important that you figure this out. So, all right? Yeah.
If something like number 10 were on the test, could we just write it as 4 times x plus 2 cubed?
Indeed, but that would be for test 2. So she just told me, isn't the answer just 4 times x plus 2 quantity cubed? Yes, it is. You know that because you know the chain rule, which is forbidden knowledge. It's forbidden jutsu. It is a secret art. What's that?
That wasn't a test, that question specifically on test 1.
Oh, I guess if you know the chain rule. No, well.
Are we allowed to do the chain rule to know it?
Yes, I suppose. But I don't think that's going to be, for those of you who don't know the chain rule, don't worry, it's not a big advantage for them. Because I'm aware of that, and for that reason, I don't ask certain questions that I would otherwise ask in a world free of people who had already taken calculus. But that's actually the point of this example, is just what you said, is that once you know the chain rule, you don't have to do this because you can just do the chain rule. It's much easier. You don't actually multiply things out. So that's the reason I'm doing this example, is so people appreciate the chain rule when we get to it. For those of you who already appreciate the chain rule, you already appreciate that this is the wrong way to do the example, which is good. It's good. Of course. Not today. Okay, so what are the other things we know? Other rules for ddx. Now, you'll forgive me, but I must give you a plausibility argument. I can't just write the rules for you. Just bear with me. So what does it mean for f to be differentiable at a? It means f of a plus h is, roughly speaking, what? It basically means f of a is approximately f of a plus h times f prime of a. And what does it mean for g to be differentiable at a? It means that g of a plus h is approximately g of a plus h times g prime of a. All I'm really saying there, guys, is that if you have functions which are differentiable, if you look at the point of differentiation, then this line is approximately the graph. Okay, so using these formulas with the h and the derivative is just using the tangent line approximation. So if I multiply these two things together, right, if I look at f of a plus h times g of a plus h, what does that give me? Well, that gives me, I just multiply these things, right? Approximately. What happens when you multiply? You get f of a times g of a plus h times parentheses f of a, well, f prime of a, excuse me, f prime of a times g of a plus f of a times g prime of a. And then there's this pesky h squared term. So I'm trying to show you. Oh well. You win some, you lose some. I haven't made it yet this semester. So my point to you is, if you look at the approximation of the function in terms of its tangent line, based at h, based at a really, the coefficient next to the h is what we is the derivative of the function. Okay? So if I take the product of two functions and I just multiply out their approximations in terms of the, what we have here in purple, then look at what's the coefficient of the h term. This right here, right? So that goes to argue that f times g prime of a is equal to f prime of a, g of a, plus f of a, g prime of a, which is the product rule, written in the prime notation. Let me rewrite the product rule in the ddx notation, in the operator notation, hopefully with a better marker. So ddx of f times g is equal to df dx times g plus f times dg dx. This is the beloved product rule. So this is something you need to know, right? Shall we try it out? See how it works? Yes, no, maybe?
Well, since we have to know it.
Since you have to know it. It's honestly really hard to illustrate why this is important to know, given that we don't have enough functions to work with in our examples. Like, we talk about the exponential function later, but we don't have that yet. Oh well.
So if you were, like for the test, would you just suggest to just work problems in the book? Because I'm one of those people who like to
Well,
problems and homework.
Yeah, of course. I mean, I work out the homework problems, and then
Set up like that?
and I would work out the.
Do that, you're doing good.
If you can do the homework problems, that's a start. But the question is, do you understand them? You should be able to do the homework problems, things like examples in class, right?
Right.
So certainly homework is most important. I mean, I would recommend that you study, yes. So I think I have posted the old tests, so you can look at those, right?
Oh, yeah, you did.
I did that, yeah.
Yeah,
I know.
just wrote a note.
They're there. Okay, so I don't know. I have trouble coming. Any example I can think of, I can solve using linearity and what we did already. So it's kind of hard for me to really get into this. But suppose I have the derivative of x squared. This is I like this example though. So this is really the derivative with respect to x of what? X times x, right? So if I look at this in terms of the product rule, I get dx dx times x plus x times dx dx. And we can think of the dx's as canceling. I mean, dx dx is 1, right? That actually is the power rule, though. I proved that with the limit earlier today. So that's x plus x, which is 2x, which of course we knew without going through this whole rigmarole. I'm sorry, I can't really give you a decent example. So let me just tell you something. Forbidden knowledge. I guess this isn't on the test because we haven't covered it yet, but goodness gracious, it's causing me physical pain not to share this with you. So the derivative of the exponential function is the exponential function, right? Now that's something that I can't, that's not a power law, okay? That's just something else. This is a new function we'll talk about more later in the course. But with something like that, it's easier to see why you need the product rule. See, because I can't just break it down to something else we did earlier today. My only really option here is product rule, right? So ddx of x squared times e to the x plus x squared times ddx of e to the x, right? Uh-oh. but I do. Joking aside, though, if you guys ever need to go places during class, just let me know. I don't mind. One thing is since we're taping the lectures, you can always catch up later. I think it's probably best for you to be here. You hear questions other people ask better when you're in the room, right? So, but you know, so this is an example where the product rule I think shines better. The first example is kind of cheesy, you know. Let me make another example up. Suppose you have a function such that f of 2 is equal to 3, f prime of 2 is equal to 7, g of 2 is equal to minus 1, and g prime of 2 is equal to 42. Calculate f times g prime of 2. This is just, this is an advertisement for the product rule. I mean, it's all it is. So fg prime of 2 is what? Product rule says that that's f prime of 2 times g of 2 plus f of 2 times g prime of 2. Let me make sure I leave myself time to go get my cookies. When's this class end? Okay, I got to step it up here. So what is this? We still got to do the quotient rule. 7. I'm trying to cover everything that's on the test today, and then we have all of Thursday left for your questions and more example. That's what I'm doing. If you hadn't caught on.
Tuesday, next Thursday.
Soon enough. Let's see here.
If it goes by this, 17 is Thursday.
Oh, right, but I need to leave you. Your homework is due Saturday, so I want to leave the next class.
Okay, just wanted to make sure it was 17th.
It's when it says, but
okay.
I try to leave one day before the test for questions, and I wanted to leave Thursday open for questions you guys have about the homework. And so there's not too much material to cover here for a day, really, if I'm not doing proofs. So, and then that's whatever it is, right? How about I don't know, what's 3 times 42? 120 plus 6, 126, 126 by 7 is 119. There you have it. Quotient rule. Of course, if you guys didn't quite glom on to what we said so far today, you can indeed ask questions about it tomorrow. So f over g, the derivative of the quotient f over g, is equal to df dx times g minus f times dg dx, all divided by g squared. Now, if you write this in the prime notation, it looks like this. F divided by g prime is f prime g minus f g prime divided by g squared. Prime notation, very, very popular with those who want to write less. But be careful. It's very easy to lose track of a prime in your work. It's much harder to lose track of a ddx. This is the blessing and the curse of the notation. Okay? So this is how we differentiate a quotient. And so, for example, what if we wanted to differentiate, let's say, x squared divided by x plus x cubed? So what we do is we differentiate the numerator, ddx of x squared. We multiply it by x times x plus x cubed. We subtract x squared times the derivative of x plus x cubed. And we divide that whole thing by the denominator squared. So we got 2x times x plus x cubed minus x squared times 1 plus 3